Hi, everyone. Welcome back to MATA02. Thank you so much for bearing with me in my technical difficulties. I am currently presenting through, for those of you who are here in person, I am obviously presenting through Zoom, so you're actually going to see everything see the same thing that everyone else does. So welcome back, and today we are going to sort of finish up most of the material for what I consider the sort of first segment of the class, where we are going to finish inventing all of the popular types of numbers that you guys all know and either love or hate from your school days. So today we're going to talk a little bit about irrational and imaginary numbers. And then in the second half of the lecture, I am going to go through a little bit of, well, quiz and homework review, since that's something that by popular request. Does anyone have any questions before we get started? Okay, great. So let's get going. Let's start off and remember, log into the chat and please put down some name that I can associate with you. If your name says anon and a number behind it, that means that I don't know who you are. Yeah, so what do mathematicians do? So we talked about this a little bit on Monday, right? So what exactly do mathematicians do? Well, some people would say that mathematicians are in the business of inventing new and clever ways of counting or measuring things. And that is sort of the theme that we've been taking in this class, right? So for that, you invent addition because that makes counting easier. And then you invent multiplication, which allows you to do repeated addition easier. And then you also have exponentiation. So like powers, you get repeated multiplication, and you could keep on inventing them, but it turns out that for most of our everyday purposes, exponentiation is as far as you need to go. And that's basically things like compound interest or pandemics exploding. So that's one of the things mathematicians do. And those, let me just remind you all what those look like. Hopefully you guys know what addition, multiplication, and exponentiation are by now. But like 5 plus 3 is equal to 8. 5 times 3 is equal to 15. 5 to the third power is equal to 125. And things like that. Notice that sometimes you have things like 5 squared is equal to 25, and minus 5 squared is also equal to 25. So things don't always necessarily map to different things. Now, another one of the things you might wonder is, well, how do you reverse operations? So that's one of the other things that mathematicians really care about, right? Well, if you can add things, well, maybe you want to do the opposite of it. So you want to subtract things. So you get things like 8 minus 3 is equal to 5. 15 divided by 3 is equal to 5. And the third root of 100, the cube root of 125 is equal to 5. But you, of course, need to be careful because it's not always unique. So it was unique for addition and subtraction and multiplication, but for powers and roots, all of a sudden you lose that uniqueness property. So the square root of 25 is equal to plus or minus 5. Although by convention, you normally use the positive one. And the last major theme of what we've been talking about mathematics. Excuse me, sorry. The last major theme of what we've been talking about mathematicians doing is, well, inventing new numbers, right? And this is sort of the scariest part of like what mathematicians do. We have imaginary numbers, irrational numbers, complex numbers, transcendental numbers, all these different names for new types of numbers mathematicians invent. Well, why do they invent that? Well, some of them are less scary, like negative numbers are invented to allow for, well, reversing addition, subtraction, and being able to still continue doing stuff. And then you also have things like fractions, which allow you to use multiplication to reverse things. So that's 1/3. And then we might have another question, which is, do we need a new number type for reversing exponentiation? So why don't you guys build on this while I look to see if we can get the technical stuff working. So do we need a new number type? It looks like people have voted. Do we need a new number type? Yes. Some people have answered no. Well, I mean, that's a defensible argument, right? You might say like, well, you don't really need new number types. You can just be all right with not everything being reversible. Like not everything has to be completely reversible. Well, mathematicians sometimes disagree with that, but that's a defensible philosophical position. It turns out, though, that I'm actually going to claim that, so things like a cube root, I'm actually going to claim that we, in fact, need more than one type of new number. And so it's by reversing roots that we get both the irrational numbers as well as imaginary numbers, which we'll get to in a moment. So, yeah. Oh, yeah, people were answering HW206. Okay, so let's keep on going. So the first thing we're going to talk about is, well, if you're going to invent new numbers, the first thing you should check is whether or not you need new numbers. And we're going to give the numbers we already have, fractions, a new name. So rational numbers. What are rational numbers? Well, rational numbers are any number that you can express as a fraction where both the numerator and denominator are whole numbers. So what you would normally think of as, well, fractions, all the numbers you can get by creating a fraction. So there are a couple of different kinds of these. So for example, even if it isn't expressed as a fraction, the number 20 is rational, even though it's not written as a fraction, because, well, things like by 2 is a fraction of whole numbers, and so is, say, 20 divided by 1. Okay? And otherwise, the number is called irrational. So, well, what about things like pi or square root of 2? That's not a real question. I know you guys have heard of these things being irrational before. Whether or not you really understand what that means, that's a different question. But here what we mean is that if it's rational, that means you can write it as a fraction. So let's think about how we can construct something that we can't write as a fraction. And of course, I've given you a hint here that somehow pi, well, pi is something that you can't write as a fraction, and we'll talk about that later. But maybe square root of 2 also can't be written as a fraction. But how would you figure that out? Well, what you might do is you might be like, well, suppose it could be written as a fraction. What then would we need to do? Well, then we'd have to find a fraction and then square it, and then get the number 2. So can you get any number and square it? Can you get a fraction, square it, and get the number 2? Well, let's see. So to do that, we really need to understand what it means to square something. So now I could say, well, to square something means to multiply it by itself. And that is completely true. But that doesn't really get at, well, why do we call it squaring? And there's actually a really good reason for that. But let's first start by writing out the sort of naive algebraic way of understanding squaring. Well, squaring means x squared is equal to x times x. Okay, easy enough. So things like write out the number line. So let's say we have 0, 1, 2, 3, 4. Let's say -1, -2, -3, -4. Well, that's an operation. 0 goes to 0 because 0 squared is 0. 1 squared goes to 1. 2 squared goes to 4. -1 squared goes to 1. -2 squared goes to 4. And so it's kind of hard to see what the pattern is, what kind of pattern is going on when you're, well, just looking at it on a number line, right? So you have things like, so that's not super duper helpful. But luckily, it turns out a lot of these things were actually invented for geometry. So now you guys have probably taken some geometry in your past. You may not have liked it too much, but you probably have seen some people drawing out figures and be like, well, if this side length is x and this side length is y, what is the total area of a square? And that's exactly what we're going to be working with here. So the issue is that somehow when you square things, you're in some sense taking it from being this one-dimensional number line, and you're putting another dimension onto it. So that's one way of interpreting it. So for example, if you had a 1 by 1 square, well, what if you call that 1, you might ask, how many squares do I have if I extend it? So how many of them are 1 by 1 squares are in, well, a 2 by 2 square? And well, you can divide this up, and you quickly see that there are 4 1 by 1 squares in the 2 by 2 square. And so that's where we get that 2 squared is equal to 4 times 1 squared. So there are 4 times as many of the little squares if you double the length of a side. And this is what we mean by squaring, because you're just taking a square with that particular side length and asking how many 1 by 1 squares you have in that bigger square. So let me write that down again. So a square with side length 2 is 4 side length 1 squares. Okay, and that's where we get this operation of squaring from. So somehow we went from measuring, well, lengths, right, to measuring areas. And in fact, this is where we also get the term cube from. So when you're cubing something, you're taking a cube with sides of that particular measurement, and then seeing how many little cubes of size 1 by 1 by 1 there are. And so there's this nice connection with how many dimensions you're looking at in space. And I'm going to go ahead and talk about what it means to have a negative length. Okay, so this is one of those things that's a little bit odd, right? But if you think about negative numbers on the number line, well, what's it like? So what do you do when you have negative, or if you multiply by -5 on the number line? Sorry, multiply by -1 on the number line. You make something negative. Well, does anyone want to take a guess? Yeah, so you flip it, right? So you're flipping it. So like you have this number line going off in both of these directions, going to the right and going to the left. Positive numbers go to the right. Then in order to, to your right. And then whenever you multiply by a negative number, it flips it and you go the other direction. So now we might wonder, what does it really mean to flip a square? Well, you can flip a square, but the square still sort of looks like a square, right? And so in order to understand what it means to flip these things, what we do is we put a direction on the sides of the square. So negative numbers are like flipping. And if you multiply by -1 twice, you want it to be the same thing. So you want to flip something twice. And one way mathematicians do this is they say that 1 is equal to a square, but where you put a direction. You're walking along the square along the side. So let's say we're going to walk counterclockwise. And so we're just saying that 1 is a counterclockwise square. And the -1, well, that would be a clockwise square. And then if you did -1 times -1, you end up back with a counterclockwise square. Okay, so this is just a sort of technical detail. In fact, this type of idea can get extended really, really far. But we're not going to go that far. We're just going to use this to try to understand geometrically what it means to have negative area. And what we really mean is you flip the square and go the other direction around the border. Any questions about that? That's actually a quite subtle advanced concept in like geometry, like this idea of orientation. Like, okay, well, let's keep on going for now. So, well, we might think about drawing out two copies of the real line, and then, well, squaring by looking at how far along on one line you go and how far along on the other line you go. So let's draw out a big 2D plane. So this is two copies. And so this is, say, 1, 2, 3, 4, and so on. 1, 2, 3, 4, -1, -2, -2, -4, -1, -2, -3, -4. Okay. And well, then we can do a 1 by 1 box. So 1 times 1 is the area of, well, this box, right? And of course, here we're going counterclockwise. And you can also do all your multiplication table this way, right? So you could multiply 2 by 3. So you could do something like multiply 2 by 3, and that would get you that box. But we're not so interested in just doing arbitrary multiplications. You could use this for that. But instead, we're interested in looking at this in terms of just squares. So what about a 2 by 2 block? Well, what does that look like? Well, that looks like this. And again, we're going counterclockwise. And one of the things you might notice is that if you take negative numbers, well, they end up being boxes down in the lower left here. And you notice that since you're flipping it twice, these still go counterclockwise. Okay. So well, when you draw these sort of shapes, you can ask, well, what that means is that we have this box of size 4. This box is of size 4, and this is a 2 by 2. This box is of size 1, and it's a 1 by 1. Is there any square such that, can you draw a box of squares such that the area is equal to 2? Well, you might be like, well, you just make the square smaller for a while until it gets to 2, and you don't keep on going until it gets to 1, right? So that ought to look something like, let me find another color. Let's see. So maybe right around here. So can you draw a box like that? So can we draw a box, a square box, that's important, box of area 2. And then the next question is, will the side, and we can call that square root of 2, will the side square root of 2 be a rational number? So these are two separate questions. So let's start with the first question. Oh, I don't think let's say A is yes and B is no. So can you draw a square of box of size 2? Okay, so it looks like most people think you can. And the answer to that is, well, we haven't really carefully defined what it means to draw a box, but sort of intuitively, we have the sense that if we just keep on making a box smaller, well, we ought to be able to get to 2 and not go too far the other direction, right? So if somehow you can move continuously, so you can continuously shrink your box, you should be able to hit 2 and stop there. Or you can start from your box of 1 by 1 and increase it and then stop there. But there's this other question of, can it be a rational number? And well, let's see. Well, at first glance, you might think like, well, even if we have the wrong number, maybe we can keep on getting closer. So for example, I happen to know that 7 divided by 5 squared is equal to 1.96. Okay, so that's not quite right, but it's getting pretty close, right? So you're getting pretty close to 2. Maybe a different fraction gets even closer. So what about the fraction 99 divided by 70 squared? That turns out to be super close. That's a 2.000204 and so on. And so somehow you might ask, well, maybe there's some fraction that actually gets there. And I see some people shaking your heads because you've seen this before in some class or another. The answer is you actually can't. And we'll prove that on the next slide. The first thing I want to mention, though, is, and this will come in handy later when we talk about complex numbers, note that we can get boxes in this grid, boxes here by multiplication, but not squaring. So these are negative boxes. And we can't get them by squaring, right? Because you notice that whenever you square something, you're always in the top right or the lower left. And we might ask, well, how do we get boxes in that region if you by squaring? And that, when we go to that particular question, that's how we'll get to things like imaginary numbers. But first, let's talk about these rational numbers. So, well, you're trying to get closer and closer. And in fact, you can get as close as you want with natural numbers, but you can't ever get them, which is a little bit odd. And really, we're getting into ideas like limits and infinity. But don't worry, we're not going to go into that in too much detail today. But let me make the claim that the square root of 2 is irrational. There is no fraction n over m such that n over m squared is equal to 2, where n and m are integers. Why is this? Well, let's give you all proof. And just as a reminder, I think I mentioned this on one of my earlier proofs. On your midterm, I will write down a proof and ask you to tell me where I made my mistake. So you should start trying to follow the logic of these proofs. So that will be one subpart of some question. So let's try to prove this. Suppose, why is my pen so thick? Can I make it thinner? No, I guess not. Oh well. So suppose there is some n over m squared is equal to 2, where n and m both integers. Okay, so what we're doing here is we're setting up to do a proof by contradiction. So we're assuming that there is some fraction, and then we're going to show that this results in something nonsensical. Well, if this is true, then that means that we can rewrite this equation as then n squared is equal to 2m squared. Okay, so far so good. And this is just multiplying both sides by m squared. You get n squared is equal to 2m squared. But now we know that n and m are both integers, right? They're both positive numbers. Well, what have we just been spending the last however many days on working on positive numbers for? We've been doing prime factorizations, right? And so, well, then we ought to be able to do prime factorizations of n and m. So, so use prime factorizations. Excuse me. So you have n is equal to, well, some power of 2. Let's call this a sub 2, 3 to the a sub 3, and so on. I'm not going to write them all out because we only really care about the 2 here. And we'll see that in a moment. And m is equal to 2 to the b sub 2, 3 to the b sub 3, and so on. So we have these prime factorizations. But then, what does that mean? What is n squared? Well, if you square a number, that just means you're multiplying. This is an exponent, so we use all our power rules, and we can just multiply each of our exponents by 2. little n squared is equal to 2 to the 2a2, 3 to the 2a3, m so on. M is equal to 2 to the 2b2, 3 to the 2b3, and so on. Okay, so that's all fine so far. But now, notice that we also know that n squared is equal to 2m squared, right? So if that's true, then that means that n squared is also equal to 2 times m, which is okay. So we have some questions in chat. If you don't know exactly what I'm doing, please just ask a question about it. But basically the idea is we're writing out the prime factorizations of n and m, and we're writing out n squared 2 different ways. Oh, that's just some exponent. So like, for example, if n were equal to 6, then n would be equal to 2 to the 1, 3 to the 1. And that would be a2 and that would be a3. So we have some prime factorization. That's just the power. I just had to give it some letter. And I gave it these complicated letters because unfortunately it's a little bit hard to, I don't have enough letters of the alphabet for, well, prime numbers if they're an infinite number of primes. Okay, so a2 is just the exponent that's on top of the 2 for the prime factorization of n, and b2 is just the exponent that's on the top of the 2 for the m prime factorization of m. Thanks everyone for putting the link in the Zoom. Okay, so now where was I? So we can also write this a different way. That's 2 times, oh, can you turn off the lights? Yes, actually I can. Is that better? So, okay, great. So we can write this other way, and then that means that this is also equal to 2b2 plus 1, 3b3, and so on. So what does that mean now? Well, that means that we know that n squared is equal to 2m squared. So now we have 2 different ways of writing n squared. And so that means that 2a2 is equal to 2b2 plus 1. Now here's where the contradiction happens. This here is even, and this here is odd. And even numbers cannot be equal to odd numbers, ever. That's just not a thing. So contradiction. And the implication is therefore that square root of 2 is irrational. Okay, so let's take a recap. How did we prove this? Well, we made use of all these various facts we've been learning in class about prime numbers. Well, we know that what we can do is any number you can write as a product of a bunch of prime numbers to serve powers. That's what a prime factorization is. So then is the second line supposed to say m squared and not just, oh, yes, it is. Yep, thanks for the catch. But yeah, so we can write this in 2 different ways. So if you could write the square root of 2 as a fraction, then you could write n squared in these 2 different ways. But these 2 different ways have to be the same because we proved that prime factorizations are unique. But now, unfortunately, when we try to write this in the 2 different ways, we end up with a power of 2 that's even for one way and a power of 2 that's odd for the other way. And so that gives us the contradiction. Okay, so this is a little bit confusing, right? And you might wonder, when did mathematicians figure out these crazy things? And so that's exactly what I'm going to ask you. So let's just give a brief reminder of what we've been going through. So, well, negative numbers were around, well, we've been through the slide many times. Negative numbers are around 200 BC to 200 AD. Multiplication was long ago, so around 4000 BCE. Direct division around the 1500s BC. The sieve of Eratosthenes, which we used to compute prime numbers, was probably around 276 BCE. And the infinitude of primes, how many there are, was around 300 BCE. When do you all think that we proved that the square root of 2 is irrational? Sorry, let me zero out the chat. So, any guesses? So is this a recent thing, or did we know this back in antiquity? Is this a crazy thing that mathematicians have only just now been coming up with, or like, are only mathematicians currently crazy, or were mathematicians always this crazy? Okay, so we have a good mix of answers. It looks like a lot of the guesses are centered around C. It's around 1000 to 1500, so like during the Middle Ages, roughly. Well, turns out we knew this in antiquity. So back around 500 BCE, this was known. It's often credited, so you guys have probably heard of Pythagoras, so for the Pythagorean theorem. So he actually had an entire school of like-minded mathematicians, and one of the other Pythagoreans, so one of the other people who followed Pythagoras, Hippasus of Metapontum, is often credited as realizing that irrational numbers existed, that you couldn't write everything as just a ratio of two different real numbers. Two different whole numbers. There are lots of stories surrounding whether, like, how scandalous this was at the time. So this is one of those things that people are like, wait, that can't possibly be right. Like, it goes against nature to have things that are irrational. Yes, mathematicians are always crazy. There's a little bit of that's true. But yeah, so even there are stories, there are apocryphal stories of Hippasus being exiled or like put to death for this discovery. They're probably apocryphal. It probably didn't actually happen, but the fact that there are these stories really does go to show you a little bit about how much people cared about this. So somehow this was sacrilegious, but it turns out to be true. So, well, so it goes. Okay, and so this was one of the, like, these are some of the simplest irrational numbers, but there are other ones, of course. So there are a few other irrational numbers that you've probably heard of. So, well, one of them is basically any root. So whenever you take a root of something, whenever you take the inverse of the power operation, you normally end up with a number that's irrational. Most of them are irrational, very few of them are rational. So things like root 2, root 3, root 5, root 6, root 7, root 8, etc. As well as the cube root of 2, the cube root of 3, the cube root of 4, and so on. Okay, so these all give you irrational numbers. If this were a number theory class, we'd prove that, but right now I'm just trying to give you some sense of mathematical history and flavor. So these are irrational, and you might wonder, well, why do we need these? Well, it turns out because sometimes you want to make a square that has exactly twice the area of a 1 by 1 square. And so you need these things for geometry. There are other parts of geometry that also give you irrational numbers. You might have heard of pi. I hope you've heard of pi. If you haven't, it's a really, really, really cool number, and there are tons of great YouTube videos. But hopefully you've heard of pi. So it's the ratio of a circle circumference to its diameter, and it's about 3.141592653 Okay, enough. I can't actually say the entire name because it goes on infinitely. Oh, yeah, so that looks, for those of you who don't know what circles are, circles look vaguely like that, and basically what we're saying is that the diameter, if you have a circle diameter 1, the length around the side is about pi. And this is super important because if you're going to, well, if you ever drive a car and you're wondering like how many rotations per minute you're going compared to like how much distance you're traveling, well, one of the ways you do that is you measure the circumference of your wheels and you ask, well, how many times are they spinning? That's imperfect, but that's one of the things you might want to figure out. And there are a bunch of irrational numbers that come from calculus. So some of you may have, and limits. So some of you may have heard of Euler's number. This can also, you might have also seen written as E is equal to the limit as n goes to infinity of 1 plus 1 over n to the n. If this were a calculus class or a finance class, we would go into this in more detail because this turns out to actually be super important for compound interest. But calculus is a little bit beyond what we're going to be covering in this class. And so we're not going to talk about this too much. But there are a bunch of irrational numbers. In fact, there are many, many irrational numbers. There are actually, even though there are an infinity number of like counting numbers, 1, 2, 3, 4, 5, there are more irrational numbers than there are counting numbers, even though they're both infinities. And if we have some time, one day I might give a lecture on the different sizes of infinity, but that is something you just have to take my word for now. Okay, so all kinds of crazy stuff. Let's give a little bit more history, since I'm trying to ground this in like the history of what how crazy mathematicians have been throughout the ages, basically. So we have all these dates about how long ago people proved like the square root of 2 was irrational, back at 500 years before the current era. So what about pi? People have known about pi for a really, really long time. But when was pi proved irrational? Any guesses? Okay, so we're getting a good mix. People now seem to think that mathematicians have been crazy forever. But the question is, even if mathematicians are crazy forever, have they been able to prove things about things like pi forever? And people have known about pi for a while. So let's take a look. Okay, so a lot of people are guessing a pretty reasonable guess. People are guessing, well, it's probably around when you prove that the square root of 2 is irrational. Well, that is actually not true. So we did not know for certain that pi was irrational until the 1760s. So even though somehow pi and the square root of 2 are both irrational numbers, somehow pi is much harder to work with. And the reasons for this actually go pretty deep, and so we're not going to be able to get into it. But the first proof that pi is irrational actually wasn't until the 1760s, and it's a super hard proof. Like there isn't a relatively easy proof that I can really give in this class. Now that I've shown you that not only have mathematicians been crazy for a while, have mathematicians been doing all kinds of weird stuff for a while, it's taken them a really long time to figure out some things that seem kind of basic. And this is one of the really cool things about math. Two problems that seem very, very similar. Like you ask the same question of two different numbers that are both pretty similar. They both come out of basic geometric ideas, like the size of a square or the size of a circle. And answering the two questions are vary tremendously in difficulty. Are any of these history facts going to be on the midterm? I am not going to expect you to memorize any history facts, but I may ask you to write a little bit about what it is mathematicians do. I'll go into, so yeah, I don't want you to memorize these facts, but I want you just to sort of understand what it is mathematicians do. The point of this course is partly to really give you a sense of what it is we do with our day-to-day. And yes, some of it's crazy counting, some of it's trying to apply it to real world things, but it really does depend. Okay, so let me give a fun side anecdote. So one of these four places, unsuccessfully, luckily, but they were halfway to succeeding, tried to pass a bill that would set pi equal to 3.2. Is it Indiana? So this is where I'm from. This is my home state of Indiana. Is it Ontario, where we all live now? Was it Kentucky? I actually used to live in Kentucky for about 6 years, and my brother still lives there. Or is it Texas, where my sister actually lives these days? So which of these places was crazy enough to try to set pi equal to 3.2? It didn't work, luckily. Okay, so I see we have people who seem to think that there's some stereotype of Texas. Let's see, are there any other guesses? So a couple people are, well, people don't, Ontario is number 2. You guys don't have very much confidence in your educational history. And a few people are saying Kentucky, and like 1 or 2 saying Indiana. Well, I am here to tell you that the answer is actually Indiana. And luckily, this bill did not pass, or I would probably, I mean, there's some chance that I would have been taught something very different in math class when I was back in school. But this was actually Indiana. So there's the, if you want to look it up, it's called the Indiana, popularly known now as the Indiana Pi Bill. So there was a physician who came up with some model of a circle. And they're like, with this new model, I can now show that the area of the circle is, with diameter 10 is equal to 32. So for the record, this actually passed the Indiana House of Representatives in 1897. So this actually passed one of the 2 houses. This was, even at the time, people were like, this is a little bit odd, especially since, as we just said, people proved that it was irrational in 1760. So, and this was 1897. So this was less than 150 years ago. Luckily, the Indiana Senate was a little bit more educated. A Purdue professor, Clarence Waldo, explained to them that you can't really legislate math, right? Like you can't just like say, I now decree as the government that pi is equal to 3 or 3.2 or whatever. That really doesn't work. But in some sense, I bring up this, oh yeah, this slide is not part of the slide deck you were given. I will put it on the next one. I just remembered this anecdote late last night and I was like, I have to tell you guys the story. Like it's super cool and it's also where I'm from. So this is my history. But yeah, but like as funny as this is, it really gets to the heart of one of the questions we've been trying to explore in this class, which is, what is math? Like, what do mathematicians do? Is it something purely invented? Is it something discovered? Because if it's just entirely a human game that we've invented, well, why can't we say that pi is equal to 3.2? And I don't really have an answer for you on that, except so far as, well, if you were to say pi is equal to 3.2, that would be bad for building wheels. And so somehow math, even if it's invented, there are like real facts about it that you can't just legislate away. And so, yeah. But yeah, so this just a fun little anecdote, and now you know a little bit more about me and where I'm from. So, okay, but let's keep on going. I think you guys have this on your slide deck. I just inserted those two slides a little bit ago. So we're going to talk a little bit about the real numbers. You might have seen it in this sort of weird notation with this weird blocky R. I'm not trying to not use that notation too often. Oh, so what we're going to say is I'm not going to formally define these things, because it turns out that in order to formally define the real numbers, you probably need to have some background in limits and calculus. You really need to have a better sense of infinity. But we can sort of intuitively think about this as, well, we have this entire real line, and of course you can write down some of the numbers, 0, 1, 2. Actually, let me write these a little bit further in so I have a bit more space. So you have things like -1, 0, 1, 2, 3, and so on. And of course, you have some other numbers on there. So you might have like -3/4, 1/2. So all these rational numbers. And you also might have some irrational numbers like square root of 2, or like pi, or e sits around here. Okay, so you can write all these numbers on, and somehow, if you could imagine that you could specify any one of these points on here exactly, if you keep on zooming in and pick a particular point on it, and any one of those points was a valid number, then that would be what the real numbers are. Now, in order to fully understand and invent the real numbers, we need a better understanding of infinity and limits and calculus. That's not the only way of inventing the real numbers, but it's one of the common ways of doing it. Let's give, because of the sort of ambiguity, because you guys probably have heard of real numbers and you probably use these things, but you probably didn't actually learn exactly how to construct them, which is quite complicated. And so you end up with questions like this, which I think was a popular social media question at some point in the last decade, or it might just be showing my age. So, is 0.9999999 repeating equal to 1? So what do people think? Let me say that this is repeating. So this is an infinite number of 9s. Okay, so we have a little bit of, oh, I feel like that would mess up measurements badly. So which part would mess up measurements badly? Like if 0.999 were equal to 1? Or if you define pi, since I don't know when that chat came on.
Like for engineers, you know, like you're building a building and you just like round it off to the next number.
Like, yeah. Yeah, so that's a good question. So the question is, are you rounding it off? And to answer this, let me first point out something, which is that when you're dealing with rational numbers, you can have two different labels that mean the same thing. So the same number can have multiple labels. Multiple labels, right? So like 1/2 is equal to 2/4. These are just like, the number isn't what you've written down. The number is somehow some place on this line. And the question is 1.0000 repeating? Why is 0 repeating more interesting than 9 repeating? One is as small as you can get, and the other is as big as you can get before going on to the next number. And so somehow, most mathematicians would probably answer yes, or they might answer that the question is ill-defined because I have not told you what real numbers are. So I've given you some intuitive sense of what real numbers are, but I haven't really told you what real numbers are. And so the question, as a mathematician, since you guys are all mathematicians in this class, the question is ill-defined. I thought rounding a number off makes it more accurate. No, so you might be thinking about rounding off to significant figures, which is something that you might do in an engineering class. That does not make it necessarily more accurate. What it does is it prevents you from thinking that you have more precision than you actually do. And this is a subtle difference in measurement error, which we also don't have time to cover in this class. But if you're an engineer, you should absolutely make sure that you understand these differences, because you don't want your bridges falling. But let me just give you one other argument that these two are actually the same thing, which is that I claim that 1/3 is actually equal to 0.3 repeating. And if 1/3 is equal to 0.3 repeating, then 3/3 is equal to 0.9 repeating. And of course, that would be equal to 1. So I should first note that you probably shouldn't be completely convinced by this argument, because we haven't really defined what numbers are, but this is the most popular argument people make to like show that these two are the same. The other way of showing that these two are the same is, what is the difference between, if you take 1 and you subtract 0.9 repeating, what do you get? Yeah. Oh, no. So let's say I said 1.000000 repeating minus 0.999999 repeating. So well, the one problem is that it's actually not, we haven't really figured out how do you subtract this thing, right? Because normally when you do subtraction, you start at the smallest digit first. But the smallest digit here, so somehow off here to infinity, you're claiming that we have a 1, but then everything after that's a 0. So you have 0.0 repeating, and there are an infinite number of these. And then the 1. And because they're an infinite number, sort of what we're saying is that the difference between 1 and 0.9 repeating is smaller than any number, right? Because for any number you pick, well, if you have an infinite number of zeros before you have any non-zero numbers, then somehow that's going to be smaller than any particular number you pick, right? And so another claim I have is that this is equal to 0. And yes, I'm playing really fast and loose with definitions here. And you really shouldn't believe me because I haven't defined what I'm doing. Like as a mathematician, you should be like, you're not doing your operations properly. You're skipping steps. And I absolutely am. Unfortunately, you really do need to have a proper understanding of limits before this all makes sense, because you really need to understand what it means to do something an infinite number of times. And I will leave it at that because this is not a number theory class where we would invent the real numbers with Dedekind cuts. Okay, but I will mention that the mathematician's answer here is probably that the question is ill-defined because we don't know what infinity means or what infinite decimals really are. And this is one of the problems that happens a lot in, well, your high school, middle school, elementary school math classes, which is that they give you all these crazy rules and then you just memorize them, but they don't really explain what's actually going on. And I'm afraid that I'm doing the same thing here because this is too complicated. But I'm hoping in this class, because we're inventing all the other numbers, or most of the other numbers, I'm really just showing you that there are reasons for all these rules. It's not just entirely arbitrary, but sometimes what happens in your secondary school classes is it would take too long to explain what these things actually mean. And so they're just like, well, memorize this because it's useful for being an engineer or useful for being a statistician or whatever. Okay, how am I doing on time? Okay, I still have a little bit of time. So let me go on and talk a little bit about imaginary numbers. Since those are also probably one of the sort of most complex types of numbers that you've seen in class. So what about square roots of negative numbers? So remember, I said that when you're undoing powers, you need two different kinds of numbers in order to do it. The irrational numbers aren't enough. So, well, first, let's recall that if you have a square, if you're squaring numbers, you only get these. You can't ever get a number over here. You can't ever get -1. Because in order to do that, you'd have to multiply a negative number and a positive number. You can't just take this number, any number on the number line get squared, because that's always positive. Yeah, because any positive number squared is positive, but any negative number squared is also positive. And so thus square roots of negative numbers can't be either positive or negative. And if you're not positive or negative or 0, well, I mean, there's no place for you on this number line, right? And so for many years, people were just like, well, that's fine. You don't need to be able to undo every operation, right? That's one of the standing arguments that we've had in this class. Do you really have to be able to undo every operation? And the answer is that well, no, you don't need to undo every operation, but mathematicians would like it if you were able to sometimes. And so to do this, we just define a new number. We're going to call it I for imaginary number. And we're going to say I is equal to the square root of -1. But now, whenever you define a new number, well, you have to see how it fits in with all the existing numbers, right? So you have a square root of -1, and maybe you also have a square root of -4. And maybe you want to call that 2i. because square root of 4 is 2, so maybe the square root of negative 4 should be the square root of -1 times the square root of 4, which is 2, and so on. So how do we do that? Well, you'll notice that we have a bunch of these numbers. So this is not on the real line, but maybe we can imagine another imaginary line. So, oh, sorry, let me use a different color for this. Let's use blue for the real line. So let's say 0, 1, 2, 3, -1, -2, -3. And let's say, let me use red for this imaginary line. Actually, is it going to, okay, good. So you might have 0i, 2i, 3i, -i, -2i, -3i. Okay, so you can imagine coming out another line. And remember, we sort of did this when we were inventing the negative numbers, right? And one of the questions we had with the negative numbers was, well, we have these two lines, but how do they work together? And with the negative numbers, we were like, oh, well, we actually just put them on the other side because it's a flipping operation. But imaginary numbers, how do they fit in? Well, one thing you might notice is that, well, 0 is actually on both of these, because 0 times anything is equal to 0. And so 0 i's would be 0. And so the way people usually do this is, it turns out that imaginary numbers, for complicated reasons, represent rotations somehow. So there's some way that you can imagine imaginary numbers as rotations. And so you often choose to represent it as a different direction that's 90 degrees offset. So that's largely convention, but it's a quite useful convention that you can justify mathematically. So you have things like 1, 2 here, -1, -2, and I, 2i here, and like -i, -2i. And then you can create arbitrary numbers. Like here, this is 2i plus 2. And so you end up with an entirely, you can also add these together, because of course, when you invent new numbers, you want to be able to add, subtract, multiply, divide, and all that. And you end up getting this entire complex plane. And so these are the complex numbers. They're a combination of a real number and an imaginary number. So things like 5 plus 4i, and so on. And it turns out we're not going to check this, but if you have the time, it would be good for you to check these things. It turns out they're complete undertaking square roots, addition, multiplication, etc. So all of these normal operations work. In fact, they work really, really well. And complex numbers actually are complete in that you can do almost all of these operations you care about and still remain in the complex numbers. So this is one of the reasons why after you learn about complex numbers, you don't really learn about other new types of numbers in school, right? And it turns out there's a good reason for this, which is that for most types of operations, you end up being complete and you can reverse them using complex numbers, even when it's not always obvious. So things like 1 plus 2i plus 2 minus I. For the record, I will not expect you to do any complex number calculations in this class. So don't worry about that. This is for your edification. So this would be equal to 3 plus I. But you notice that you can just treat the I as sort of like an x, right? And then you just add these things together. But when you multiply, it's a little bit more complicated. So 1 plus 2i times 2 minus I. You use FOIL, you get 2 minus I plus 4i minus 2i squared. Well, of course, 2i squared is minus 1. So this is equal to 2. These two things give you plus 3i plus 2, because that's minus 2 times minus 1. And so this is equal to 4 plus 3i. So even when you multiply together, you get I squareds or you get I cubes, but those still end up being complex numbers because you can take the I squared and bring it back down to a minus 1. And lastly, I will just point out that the square root of I is equal to plus or minus 1 over square root of 2 times 1 plus I, which is also a complex number. You can multiply this together and check to make sure this is true, but we're not going to worry about that. So somehow the complex numbers complete most types of operations. And yes, some of this looks like black magic until you actually sit and work through it. And let's see, what else? So let's talk a little bit more about history, because I want you to get some flavor of this. When were complex numbers invented? Let me zero out the chat. How long did these take? Imaginary and complex numbers. We talked about all kinds of other numbers we've been inventing. So is this more recent? Is it earlier? Okay, so people seem to think this is pretty recent. Okay, oh, no, it's not that recent. So 1500s to 1800. Okay, so this might be one of the first times in a while for these sorts of history questions that you guys have guessed correctly. So this was from the Ars Magna, so the great work in 1545 by an Italian professor, Cardano. And so this is when imaginary numbers were really written down. Like people had like come across them in the past, but they were like, well, this doesn't make any sense, and they just ignored them for a while. But it turns out that they're useful for some purpose. And so does anyone want to guess what these were useful for when people first invented them? Just guess in chat. Or you can just shout it out at me. What do you guys think these crazy kinds of numbers were useful for? Knowing how crazy mathematicians can be sometimes. Do you think people did them for some type of engineering application, some type of thing they were building? Or do you think mathematicians were just being super weird and like coming up with numbers randomly? Why Len? Thinking about space, weird, medicine, counting flowers. I think you guys need to think a bit weirder. So it turns out that no, you're thinking all way too practical. Mathematicians used to have duels. So what people would do is a mathematician would challenge another mathematician. They'd both get up on stage in front of an audience that would be cheering or jeering and all that, and they would give each other math problems, and then they'd have to try to solve them on the fly. And whoever was able to solve more math problems more quickly would win. Yes, bragging rights, basically. So these were mathematical duels in Italy in the 15th and 16th century. And so I actually, bring that book. So I actually have a book on the history of the square root of -1. So on the history of imaginary numbers, which goes into like the story of like these big mathematical figures who would come up with new mathematical techniques, and they would often like almost take them to their grave, because these would be their secret. These would be their secret weapons whenever they were challenging other mathematicians to duels for bragging rights. And it turns out that using imaginary numbers, even when the final answer is real, sometimes you need to use imaginary numbers to find the answer. And so Cardano, I actually don't know how long a duel would be. I think often they would like give each other like 10 questions or something like that. It's been a while since I read this book, but it is something you can look up online, and it's a kind of cool story because I think it really humanizes mathematicians a bit. Like we're not all just people in some ivory tower trying to figure stuff out. Like, well, people like bragging rights too. So, and often they would be these questions like 5x cubed plus 2x is equal to 3. They'd be these cubic equations which are really, really hard to solve, but people were able to. Now, okay, so that's why they were invented. They were basically invented for like competitions. But in the modern day math, complex numbers are really important whenever trigonometry appears. And this, if you ever talk to an electrical engineer, it turns out that complex numbers are super important for understanding how electricity works. So even though these were invented purely for bragging rights and for competitions, they do actually have a very real application to the way our electric circuits work. Because if you think about electric circuits, often the signals come in waves. And things that are waves are sort of like trigonometry, sine, cosines. And whenever you have those, imaginary numbers become super useful. And with that, I will go ahead and end the first half of lecture. Let's have a, let's say 10-minute break. So be back at 10:18. In the second half of the lecture, we will be talking about, it will just be a review of the material that's on your assignment and quiz. And so I will be going through computations with y'all. So 10-minute break. Feel free to do whatever. Also, feel free to take some more candy if you want, if you need a bit of a sugar rush, because it is early in the morning, and I know I'm not fully awake, so I can only guess how awake you guys are, especially with the lights off. Let's turn them on for the break.